So the one other thing is that you know that different metals have different ionization energies. They hold on to their electrons with different electronegativities, to different strengths. And so, anyhow, because of that difference, some electrons will more easily leave the piece of metal, some less likely, and that value, the value that represents how tightly, how much energy is required to kick off the first electrons. All right. Now you can exceed that and kick off a whole bunch, but you have to at least get up to a certain energy level for the electrons to have enough energy to kick off in the first place. All right, to exceed that, again, that ionization energy, how closely held those electrons are to the metal. What is that per metal? And there's a table on page 879 that has these in there. It's called the work function. I don't know who came up with that name because it doesn't seem like it describes this very well. They use the Greek letter phi for that. And that represents, again, that's going to be an energy level in electron volts. And that is the minimum amount of energy required to just get electrons to leave that metal. It's the minimum amount. If you're right at the work function, you're actually not going to get a current. It's that cutoff point, right? Where you've got to, any less than that, you're not going to get anything. If you exceed it, you're going to start to get a current, all right? So if you put this back to just 0, so there's no charge here. Okay, so the power source isn't doing anything, all right? It's not positive or negative. Then you need to exceed the work function to kick off from, so the light will come here, the electrons will absorb the energy of the photon, and we say they totally absorb it. They totally absorb that. So now they've absorbed that energy, giving them some kinetic energy. If that energy exceeds this for the metal, this is for the metal, if it exceeds that for the metal, then they will start to leave the metal and flow, okay? So, the maximum kinetic energy of these photoelectrons is going to be the difference between the energy that they absorb, which is HF, less the energy required to leave the metal. That's the work function. So this is the energy they need to leave the metal, okay? If these two are the same number, then they're not going to have any kinetic energy, all right? But if this is greater than that, then they're going to have a little bit of energy left over. First, they have to spend their energy to overcome that, to get away from the metal. And so if this is a little bit bigger than that, they're going to have a little bit of energy left over, and that's going to be the kinetic energy that's left over allows them to make it to the other side, okay? And that will start to flow in a circuit, okay? So you need to know the work function, or you're going to be given enough information to calculate it. And then remember, this is the energy of a photon. And let's just define a couple things. Okay, again, this is the kinetic energy of the photoelectrons. Photoelectrons. That's this. This is the energy of energy absorbed from the photon. Energy absorbed from, it's by the electron from one photon. And that's the energy spent getting away from the metal. The energy required to get away from the metal, and then it has to use that energy to get away from it. So that's the work function. That's the energy. This is an energy equation, all in electron volts. All right, energy needed to get away from the metal. This is probably really hard to read, and I apologize for that. So the energy needed to get away from the metal. Let me read this to you in case you can't read it. So you've got the maximum kinetic energy in this equation. That's the kinetic energy of the photoelectron. These things. All right. How do you get that value? Well, the electrons that are on the metal, the valence electrons, they're hit by photons of light. and the photons of light are absorbed by the electrons. That's this. And this is the energy required to get away from the metal, all right, what we call the work function, all right? If that is greater than that, then they're going to flow with whatever remaining energy is, the difference between the two of them, okay? This is a really important equation. I'm just going to erase this stuff because it's getting awfully messy. Ke max equals HF minus phi. Okay, important equation. It's on the equation sheet. Now, actually, I think more useful than this, although that's the one you want to remember, it's written like this: Ke max equals HC all over lambda minus phi. All right, doing a little substitution there. When you graph this, again, you'll see this graph in the textbook. When you graph kinetic energy on the kinetic energy, Ke max, so this is your y variable, Ke max right there. Actually, I need to go down here. And then frequency is going to be on the on the x-axis. This is linear, where the slope is h, so that's your y variable, that's your x variable, this is your y-intercept, and that's your slope. It's linear, so it looks like that. Again, the slope equals h, right? Now, there's a point. This is 0. This is interesting. So this is high frequency. You start lowering the frequency. You start getting to lower and lower colors, down to red and then maybe infrared, whatever. You start going to lower and lower frequencies. You're shining light onto this piece of metal, and then eventually you reach a lower frequency where you no longer get any current. So that would be zero. So zero kinetic energy means it's no longer getting across, right? High frequency, great, because the reason why that makes sense, the higher the frequency, the higher the energy, right? Energy equals h times f. The higher the frequency of light, the more energy the photons have. But as you decrease the energy, eventually you don't have enough energy to overcome the work function, and you no longer have any flow. That is called, this point right here is called the cutoff frequency, F subscript C, all right? Cut off frequency, okay? And the corresponding wavelength is going to be lambda C, all right? And so the cutoff frequency and then the corresponding wavelength would be lambda subscript C. Now, you don't really need to do this, but as you go down here, that would be -5, right? Your y-intercept. But normally when it's graphed, it stops right there, okay? This graph is important. You definitely want to know that right there. Okay, the next thing we're going to do, I'm going to stop this because YouTube only lets me put on 10 minutes at a time, and then I'm going to do an example, all right?